Hello, I'm Michael Baron from American University. And as you can guess from the first slide, I will be talking about quality control in semiconductor manufacturing. The first part of my talk is based on my collaboration with Texas Instruments in Dallas, Texas. Second part will be based on the one wonderful year that I spent at IBM Research Center, collaborating in particular with our dear session organizer, Emmanuel Yashin. You know, nanotechnology, we're getting thinner and thinner, and every year new chips are being manufactured with thinner and thinner layers. So as far as I understand, in 2017, the thinnest layer of circuit was 7 nanometers. In 2018, Samsung came up with 5 nanometer technology, and next year, in 2021, they promised to start manufacturing 3 nanometer layers of chips, which is about 30,000 times thinner than the human hair. And as you can guess, this technology is very delicate. What you see are clean rooms. The people there are only to observe and correct the process whenever needed. All the operations are done with very expensive and very advanced robots. It's so difficult to do any operations on such a small nanoscale that no process can completely avoid defects. Defects always occur in semiconductor manufacturing. You can see the actual lot. I will not tell you where this lot is from, but the black points, black dots on these wafers are defective chips. So this lot, like many other lots, contained 24 wafers. Each wafer can have several hundreds to several thousands of chips or dice. These are small squares with millions of resistors, transistors, capacitors, the whole complicated circuit packed in often less than half a square inch. So our goal in the first part would be to capture the patterns. You can see some kind of patterns. The chips are failing not completely at random. There are very special relations between defective chips, and we would like to classify these special patterns and provide troubleshooting, relate what we observe and quantify to possible problems, possible causes, root causes, what could cause these failures. You can see these are generated patterns. These type are diagonal patterns. These are vertical patterns, but on the second wafer, they are not as strong as on the rightmost wafer. At the time when we started working with Texas Instruments, I was a beginning assistant professor, interested in everything. The most popular method of determining root causes was just visual inspection. What you see are called wafer maps. Often these wafer maps were colored. They could not only point where the defects are, but also color them by the type of defects. Then a very experienced person looks at the wafer map and says, aha, that was misalignment or some other problem. But this visual inspection is not reliable. It requires human and it is slow. It was designed to create some automated system that will classify the patterns and provide quality control. So first of all, we need a good model that will capture special patterns and return a likelihood. All our analysis in the first and second part will be likelihood based so that we can estimate parameters and know exactly what these parameters mean and how they're reflected in good and defective chips, and ultimately in the total yield. So the model that we chose is a Markov random field model. It's a generalization of a Markov chain. You know, in Markov chain, the future depends on the past only through the present. In Markov random field, every chip depends on the rest of the wafer through its neighborhood. We define the neighborhood. Neighborhoods can be simple or complicated, and they will generate the whole Markov random field model. So the neighborhood is a set of chips surrounding our given chip. This is a notation. So by W, I will denote the wafer that consists of chips, and each chip is good or bad. So 0, 1. We have Bernoulli data, correlated Bernoulli data on a surface, on a wafer. Q is a neighborhood of a given chip. Now, let's take the simplest neighborhood that comes to the mind. Let's include the chips just above and below, top and bottom, right and left of a given chip. This is called an autologistic model. You can find it in literature. And this is quite simple and tractable. However, we've seen diagonal patterns, and they do occur on real wafers. This neighborhood structure can only capture vertical and horizontal correlations. So we need to make one step further and consider what we can call king move neighborhood. A chess king moves into one of these squares, or just 8-unit neighborhood, including the diagonal neighbors. Our target will be to try to get the joint distribution of all defective and good chips on a wafer, which we will see will be quite impossible. Not because it's complicated, because it's not tractable. It includes a term that is not tractable, and we will see it. So therefore, what is remaining for us to do? We can, instead of a joint likelihood, we will consider conditional likelihood. Conditional distributions are available, and that's what we will use. Our parameter estimation routine will be based on conditional probabilities, and then we will find a way to connect parameter estimates to the root causes. So the theory of Markov random fields says that the distribution is expressed in terms of clicks. Here is the concept, a click. A click is a perfect graph. It's the set of chips where each chip is a neighbor of every other chips in the click. So you can see that according to our neighborhood, there are 10 types of clicks, from a single point, which is a simple, trivial click, to the largest click of 4 chips. There cannot be any click larger than that, because if you add another 5th point, wherever you choose it, there will be 2 points that are not neighbors of each other, and therefore this will not be a click. Well, next notation, for any sub-neighborhood of our neighborhood, omega will denote a logit of a probability that a chip fails, given that the sub-neighborhood completely fails, so is 1 for the whole sub-neighborhood, and the remaining part of the neighborhood consists of good chips. Zeros are good chips, non-defective. So with this, we can consider different examples. The trivial example is when the whole wafer consists of good chips, and we are looking at the probability for one chip to fail. So this alpha will be the logit of a probability for this chip to fail, given that all its neighbors are good functioning chips. This is the pure failure rate. It's a logit of conditional probability to fail if all neighbors are good, so the chip fails by itself, not because its neighbors failed. Next, consider omega of the right neighbor of our chip and subtract the previous logit alpha, then what we get is the additional logit. Additional logit due to the failure of a neighboring chip, either the neighbor from the right or the neighbor from the left. Similarly, we can define an additional logit due to the failure of top or bottom neighbors, or simultaneous, the diagonal neighbor, the neighbor on the right bottom or right top of our chip, left bottom or left top. So this will be two new parameters capturing diagonal interaction, nu and pi, along two diagonals. Next will be the additional logit due to the simultaneous failure of two neighbors, from which we subtract the previously defined logit. So this will only be the additional logit. And finally, the 10th parameter. So overall, there are 10 parameters. The 10th parameter is additional logit of the probability for the chip to fail, given that 3 of its neighbors failed, so that all 4 neighbors form a clique. So we have 10 parameters of our Markov random field. Corresponding to these 10 parameters, there are 10 cliques and 10 statistics. These statistics represent the counts. So corresponding to alpha and sub-alpha is just the pure number of defective chips. And sub-lambda, lambda was the clique that captures horizontal interaction. So this will be the number of pairs of horizontal neighbors that simultaneously fail, right? This product is 1 only if both variables are 1s. I'll remind these are Bernoulli variables, etc., etc. So each statistic is the count of defective chips corresponding to the given clique. Say n theta is the number of cliques of type theta consisting of 3 defective chips. With these parameters and statistics, we can start developing the likelihood. Hammersley-Clifford theory helps us in this. It's all based on the pretty famous but unpublished 1971 manuscript of Hammersley and Clifford. By Hammersley-Clifford theorem, the joint log likelihood has to have this form. It's a linear function of our statistics. What are the coefficients of this linear combination? G alpha, G lambda, etc. We can find these coefficients from the factorization theorem. The factorization theorem by Hammersley and Clifford connects two wafers, wafer X and wafer Y. Apparently, we can go from one wafer to another wafer step by step, just changing the condition of one chip at a time, replacing a good chip with a defective chip or defective chip with a good chip, and taking the product of the corresponding ratios. So we will use this factorization theorem repeatedly to find step by step each coefficient G. We'll start with G alpha. One wafer in the denominator will be complete 0. So a wafer, an ideal wafer. I have never seen an ideally perfect wafer. So this 0 is the wafer consisting of all good chips, and compare it with a wafer with just one defective chip. Then what we have here, all the counts are zeros, because you will never find a clique consisting of all defective chips if you have only one chip, except alpha. So there will be only one count for the alpha. So on one hand, this will be just 1 times G alpha. On the other hand, this is precisely the logit of a probability for a chip to fail when all the neighbors are good. So this is alpha. So we found the coefficient G sub alpha equals alpha. Just as simple as this. Next, we'll compare 0 wafer with a wafer consisting of 2 defective chips that are horizontal pair, horizontal neighbors, and all the other chips are non-defective. Then we take the ratio. there will be 2 defective chips, so n alpha is 2. There is 1 horizontal pair of defective chips, which is n lambda. So we have 2 alpha plus 1 times this unknown coefficient g lambda. But this lambda is precisely the additional logit. So we find g lambda, and it must be equal to lambda, etc., etc. And we find out that all coefficients g just simply equal to the corresponding parameters. Perfect. Then we can write the joint distribution, and our problem is almost solved. This is the entire distribution according to Hammersley-Clifford theorem, right? So this was log. To get the distribution, we take exponential. So we are done. Well, it includes P of 0, right? This P of 0, probability of that ideally good wafer, no defects. Well, how do we find this coefficient? This is a normalizing constant, right? So the normalizing constant should include the sum over all possible wafers. Imagine what it is. The wafer consists of hundreds or thousands chips. Each chip can be good or defective. So it is how many terms in this summation? 2 to the power, and the power is the number of chips on the wafer. Let's say 2 to the 300. No, that's not feasible for us to compute. I think even quantum computer will not be able to do this computation. However, can we just drop the constant? No, it includes unknown parameters. So it cannot be neglected. It's not computable. So we cannot use the joint distribution. We can deal with conditional distributions, though. That's our solution. Conditional distribution of any chip given its neighborhood is here. There is a closed form formula. In terms of these deltas, what is a delta? For any click C, any of these 10 types of clicks, and any chip S on a wafer, delta is the difference. Basically, it's the additional number of clicks of type C if a defective chip S turns to a good chip, or its negative additional number of clicks of defective chips if a defective chip, if a good chip becomes defective. Then it will be the additional number of such clicks, right? So we have the formula for the conditional probability. How are we going to use it? Well, we cannot construct the likelihood, but we can construct a pseudo likelihood. So pseudo likelihood will be a product of conditional probabilities along the subset of our wafer, where indeed these chips are conditionally independent. You see, with our type of a neighborhood where we only take immediate neighbors, horizontal, vertical, and diagonal immediate neighbors, if you select every other chip on every other row, then indeed they will be conditionally independent given all the other chips, right? Because the other chips will constitute the neighborhoods of these selected chips. Once again, every other chip on every other row. So we can indeed multiply conditional probabilities. They're conditionally independent. And then when we maximize this with respect to theta, theta is a vector of all 10 unknown parameters, then we will get maximum pseudo likelihood estimates. Very good. Well, very good, but we used only 25% of data. Every other chip on every other row is a quarter. We're losing 75% of sample size. So it's not a very good solution. There is a way out. Why don't we multiply all of them? This sounds like complete cheating. You cannot multiply them. They're not independent. Yes, I agree, they're not independent. However, well, this was proposed long before us, and comments proved that maximum generalized pseudo likelihood estimators multiplying all conditional probabilities across the whole wafer will be called generalized pseudo-likelihood. Maximum generalized pseudo-likelihood estimators also possess nice properties like the usual MLE. They are consistent, asymptotically normal, and here is the paper that proves it. So why not? And especially recently we noticed that if you expand this likelihood, this is nothing but logistic regression. And indeed, all the software estimate parameters of logistic regression by maximum likelihood method, right? Not by least squares. So if we just use logistic regression, regressing every chip on the deltas generated by its neighborhood, on those deltas, then the slopes of this logistic regression will give us the unknown parameter C. So C belongs to theta, so C is one of these parameters, alpha through kappa. I can call it logistic autoregression because it regresses each chip on other chips in the same wafer, right? So once we go through this estimation, well, here are several applications. Well, first of all, we can find, convert logit into probability, and this will be the probability for a chip to fail. This is like a pure failure rate. Probability for a chip to fail due to its defects, not due to the failure of neighbors, pure failure rate. The next batch of parameters show us the most typical clusters, shapes, thickness, direction of clusters. Direction is identified by these vectors. The thickness of clusters is determined by the relation of these parameters. If the horizontal and vertical parameters are close and diagonal parameters are also close, then you will have round type of clusters. If diagonal parameters are smaller, you will have kind of diamond. If they're bigger, this round cluster circle becomes more like a square, or rectangle if lambda is not equal mu. So you can find the most typical shape, size, thickness of clusters. You can classify several patterns. There are some degenerate patterns where, say, all the deltas are positive. Then the horizontal, if one chip fails, then all the horizontal neighbors also fail, like a chain reaction. Or non-degenerate when defective chips seem pretty random. What we actually implemented in Texas Instruments, and our research assistant was hired by TI, and I think he's still there, a senior statistician, watching our algorithm working. So we used our 10 parameter estimates as the input for artificial neural network. The output was the one of possible root causes. And without finding the explicit relationship, artificial neural network is trained using 388 wafers representing all the known root causes, where I think the last one was called unknown. It can classify to that one as well. F-test shows very significant relationship. Here is a p-value. And the algorithm classified the testing data, 675 different patterns, correctly out of 780. That is about 87% classification rate, and this is much higher than any visual inspection. So to conclude the first part of this talk, this algorithm, of course, it aids practitioners, the engineers. It completely automizes the process of determining root causes. Whenever it knows what the root cause is, the engineer can get this information to see how the process can be corrected. And this proposed automated classifier, including generalized maximum pseudo-likelihood parameter estimation and artificial neural network, replaces visual inspection of wafer maps, and it guarantees a higher classification rate, higher rate of correctly classified wafers. We can make one step further. This is the most recent development. You see the wafers, as I already said, are produced in lots of 12 or 24 wafers in each lot. And if you look at the wafers from the same lot, you can see that the patterns are pretty close. And this makes sense. You know, the robots are taking one wafer at a time, doing some operation and putting it back. If something goes wrong, some misalignment, some misprocessing, or maybe there is a lack of some chemical, or the temperature is not right, then any pattern of defects can propagate through the lot from one wafer to another. So far, our Markov random field was purely two-dimensional. But now we can add the third dimension and see if there is any correlation between wafers within the same lot. So this is another type of neighborhood that we considered. Long after I finished with TI, this was just for us to try. This generates a three-dimensional Markov random field. So any chip is related to the neighborhood on the previous wafer and on the next wafer in the lot. You wonder if this third dimension is significant. So how do you test significance? Well, since we have the likelihood, actually not exactly likelihood, but generalized pseudo-likelihood, then we know how to test hypothesis about zero interaction, zero slopes. We just need to take the -2 log likelihood ratio. And the literature says that under the null, this will follow a mixture of chi-square distributions, which is not so easy to fit. However, we tested against the pure chi-square. So we're testing 4 parameters, assuming left and right correlation is the same as left and right are the same, up and down correlation are the same, and 2 diagonals are also the same. So there is a chi-square with 4 degrees of freedom. There are 4 parameters that we're testing here. You see the empirical values are very close to theoretical chi-square distribution. So we think that chi-square would be quite an adequate distribution to use. Well, if this was a live talk, I would have asked for any questions. Since I'm just recording and talking to myself on this wall, here is my email. So please, if you have any questions, comments, counterexamples, disproving everything, please email me at this address. And I'm going to the second part of my talk. It's based on our work at IBM, and we called it Wafer Tomography. So tomography means recovering, reconstructing what's hidden in the wafer based on only what we can see. And what we see there, we will, unlike TI, where we only, in the first part of the talk, we only considered good and defective chips, zeros and ones. Now we're going to go inside the chip and use the layer by layer information on defects to predict the quality of chips. So good and defective chips will be our output, the response. We would like to relate chip defects with chip failures. We would like to predict the yield, find probable root causes, defects that caused the chip to fail. We want to determine the most dangerous defects, the most dangerous combinations of defect and layer, the most vulnerable layers, and ultimately suggest the optimal business strategies. IBM can invest and work on certain type of defects and reduce either the size or the frequency of certain defects. So it's important to know which defects are making the most impact to see which ones are most reasonable to reduce. So the wafer consists of layers, and on each layer, defects may occur. You saw how delicate and how tiny, small, nano-scale process this is. So we would like to take the observed defects and somehow relate them to the probability for the chip to either operate or fail. In this, we will assume that failure of a chip can occur by defects or by other causes, and the other causes are specific to a lot. That any defect can be fatal with certain probability. Probabilities are different, but the impact of each defect on the condition of a chip, we consider them independent. We assume that the number of defects of any type on any layer are Poisson with different frequencies, different parameters. Parameters are specific to the defect type. There are more frequent and more rare defects, specific to the layer, and specific to a lot. Then let's start with one chip and say the probability of survival of this chip is a certain function of three things. R of J is the effect of defect type J. L is a layer, A of L is the effect of a layer or operation. Manufacturing of a chip is a stepwise process. There is a long sequence of steps or operations. So L can be an operation or a step. And it's a function of S, the size of a defect, small defects or large defects. The function of a size, we chose log of 1 plus S, and it took us some weeks of experimenting with different functions. So both equations 1 and 2 are suggested empirically based on the analysis of many, many wafers. And we acknowledge that when Samsung comes up with a new type of chips in 2021, one should revise these equations and maybe come up with something that fits better. For every new mode of production, probably these models should be reassessed and reevaluated. Well, this would be very easy. We already assumed independence of chip failures based on different defects. So we can just multiply out these probabilities and we are done. However, most of defects are not classified. Only a small portion of defects will come along with the class, what type of defect it is. So most defects remain unclassified. And then probability of survival, well, we can still find probability of survival given the size of a defect. And this is nothing but a formula of total probability where we need to guess the type of defect given its size. It's a conditional probability that can be found using a Bayes formula. This will also include the distribution of sizes. So we need some distribution function of size S that we will estimate, of course, from the real data. So we get this probability of survival or probability that the chip survives some unclassified defect of size S on level L. However, so this is the resulting probability. However, most layers are not inspected. It's too slow, too expensive to inspect all the layers. So 75% of layers remain uninspected. That is, the layer exists, it's there, but we know nothing about it. We don't know how many defects are there, what types, what sizes. It's dark space. We don't know. So we cannot ignore them, right? The fatal defect, the defect killer that killed a certain defective chip, can be on one of these uninspected layers. So we cannot just ignore them. Instead, we will also use the formula. It's basically also a formula of total probability that is a sum over all possible numbers of defects of each size. So this is the number of defects on chip I, defects of type J on layer L of lot M. That's what the indices mean. So this is what we come up with. It's the moment generating function, right? It's probability of a survival of a chip, that it survives all the type J defects on layer L to the power n. So it's this probability, some function psi to the power n. And we can take this power because we know n is Poisson. We assumed that the number of defects is Poisson. So we just take the moment generating function of Poisson distribution. And this is what we get. So now we accounted for observed and classified, observed and unclassified, and unobserved defects. And overall, we can build the likelihood function. Well, it's not very short and it's very far from being simple, but we can still write it. It includes phi I, so all these pieces of likelihood derived before are in this phi I, the probability for a chip to survive all the defects. The previous part of the likelihood corresponds to the probability of all these defects to occur, including also the effect of other causes specific to the lot M. So here is our likelihood. Well, we need to maximize this likelihood. However, you know how many parameters we have. So the chip will have maybe 40, 50, 60, 70 layers with defects of 40, 50 types. We can have hundreds, thousands of lots. And therefore, we have, let's say, 50 times 50 times 100 different defect frequencies. Overall, this is more than 100,000 of parameters. No computer will do a maximization of that dimension. So what do we need to do? And this is, of course, not counting the distribution function of defect types and the function, the transformation of defect sizes. That also need to be estimated. So what do we need to do? Well, there is a standard method, EM algorithm, and here it comes very naturally. So the E step will handle most of the parameters. Most of them come from these frequencies, defect frequencies that are really dependent on the layer, defect type, and lot. We can update these frequencies. This is a frequency, the expectation of a Poisson variable. So we can update them as the expected number of defects of type J on layer L, given what we already know, given the size of defects. So this is the re-estimated number of classified, unclassified, and unobserved defects divided by the total number of chips. This will be the frequency, the new estimated number of defects per chip. And the remaining parameters, there are much fewer of these parameters, A, R, and B, can be estimated by an M step maximization. So in practice, the E step will take minutes. The M step may take hours. Of course, depending on the size of your data, we handled hundreds to thousands of lots with 24 wafers on each lot, hundreds of chips on each wafer, etc., etc. So in a few hours, the algorithm can converge. However, you know, it's so difficult to fit the distribution perfectly. In practice, the data are so messy. We would love to have a nice paraboloid looking, maybe like this, paraboloid looking likelihood with unique and very clear maximum, and that will be our maximum likelihood estimator. But in fact, the surface, the likelihood will be wiggly, will have some local minima and maxima, and it's very possible, depending where you start your iterations, it's very possible that the EM algorithm will lead you to a wrong maximum. So how to handle it? Well, Emmanuel proposed the new D step, directional step. We will only make an iteration if it results in a larger likelihood, where after the maximum likelihood. So once we estiblish the direction, and the direction is just the segment from the previous to the new estimator of our parameter theta that consists of all our parameter estimates. So when we see, as a result of the previous E step and M step, that the estimator goes to that particular direction and the likelihood is increasing, then we can just continue going in the same direction, making a longer and longer step. Anyway, we will make this step while the likelihood increases. If it ceases to increase, we will stop moving into that direction, so we're not losing anything. However, it will shake the system and move it away from a local maximum. So in practice, we only needed to apply this step once or twice. You can see that it made a large D step, or a sequence. Each D step consists of a sequence of steps going into the same direction. And you see how much it reduced the negative log likelihood, right? We need to reduce it. And after that, the D step was not even needed. The E step and M step did not make much changes, and after 9 iterations, it all converged. Here is our relative prediction error and prediction ratio. So these are performance characteristics. What is the prediction ratio? What will tell us whether we did a good job in our prediction of yield or bad job? Well, it's a good job if we have a ratio significantly bigger than 1, the ratio of yield predictor on really good chips and yield predictor on really bad chips. Okay, so we can, since we know in our data, we know the condition of chips by the detailed engineering analysis, we can find these yields. Well, a little theory about these yields. So this is the first and most natural application of everything we're doing is predicting yield of our production. So for each chip, we can estimate parameters and use them to predict the survival probability that the chip will operate. And for the whole wafer, the yield is the average of these probabilities. So how good is our prediction, or any other prediction? Can we really compute this yield estimate for all the good chips and all the bad chips and achieve 100% yield prediction here? That would be ideal, to predict every good chip as being good and every defective chip as being defective, just based on the observed defects on this chip. Can we make them 100% and 0%? Well, there is one theoretical result that we were able to prove. If we have any Bernoulli variables, here they correspond to good and defective chips. But in the theory, we can talk about any Bernoulli variables. Then we compute this yield ratio, the yield estimate for good and bad chips, or yield estimate computed on all really Bernoulli variables that really equal 1 and those that really equal 0. And we proved that the strong law of large numbers will hold, and that will mean that when we have a large number of observations, and here you saw the number of chips is pretty large, these are the limits of our yield prediction on good and bad chips, on real ones and real zeros. And the difference between them has a limit, and the limit is not 1, because we have some variance of survival probability in the numerator. So this is the strong convergence with F probability 1. So how good this is? Can we make 100% ? No. These are the limits. This is the best that we can achieve. Other applications. We use the estimator parameters to estimate kill ratios. This is not our term. Kill ratio is a known quantity in semiconductor manufacturing. So this is the probability that a given defect of type J on layer L kills the chip, appears fatal. This will be the formula. Similarly, we can compute the arbitrary type J defect wherever it appears. Let's say it's a puddle or a short. On whichever layer it appears, this is the probability that it will kill a chip regardless of a layer. It's, again, a formula of full probability across all layers. Or just probability that any defect kills a chip, the overall kill ratio. We can estimate causes of failures, CF. It's a probability for a failed chip. Given that this chip failed, what's the probability that this defect is at fault? It's the detective action. When you have a murder case, the chip is already murdered, you are looking for a killer. So this cause of failure is probability that a given chip is a killer, killed a given defect killed a chip. What we're using here is a group kill ratio, and the group kill ratio is probability that at least one chip killer is among all type J defects on a given layer. So this is the probability that this given defect is the cause of failure. Next thing is what we call sensitivity. So as I said a few minutes ago, IBM can make an investment and reduce either the frequency, lambda, or the size, S, of a defect by a certain percentage. Let's say it reduces the frequency by 100 times alpha %. E is a sensitivity if this reduction results in yield improvement by alpha times E %. So that is the sensitivity E to the changes in the frequency of defects. And similarly, F is a sensitivity to the reduction of the defect size. If the size of a defect is reduced by 100 times beta %, then 100 times F times beta % is the resulting improvement in the final yield. So to conclude this part and the whole talk, we developed a tomographic model that relates chip failures to the defects occurring on a chip. It can work with a pretty large dimension using EM algorithm with the additional D step, EMD algorithm, if you'd like. We can use it for yield prediction in the end of the production line or anywhere in the middle of production. So that's pretty useful to be able to estimate the final yield before certain layers are produced. If the final yield estimate is very low, then maybe it's more reasonable to just scrap this chip and not produce it any further. Maybe we can scrap the latest one of few layers and rework them, hoping that the final yield will be improved. We can estimate kill ratios, causes of failures. We can do sensitivity analysis, and matching this to the real cost of size or frequency reduction, we can develop the optimal business strategy, whether it's reasonable to beneficial to invest a certain amount to reduce the size or frequency of defects by a certain %, knowing what yield improvement this will result in. So here are some references, and this is a joint work with Emmanuel, of course, at IBM. Asya Taken collaborated with us. She's now at Alliant. Lakshmi worked with me at Texas Instruments, but now he's in Teradata and UT Austin. Zhenwu Chen is still in Texas Instruments, and Zach is our student at American. Thank you very much.